Okay, so you've survived upper bounds and now we're going to move to lower bounds. This is where it gets a bit more difficult, and that's because lower bounds are rather more abstract. In upper bounds, we're looking at mechanisms. We can imagine things failing and things moving, blocks of soil moving around. But in lower bounds, nothing's moving, nothing's failing. It's on the point of failing. So it gets a bit more abstract, what we do. And that makes it rather more difficult for us as engineers, where we like to imagine things failing or falling over or something. So people generally find this much more difficult, even if the mathematics is not so tricky. It's okay. So here we are. We're going to deal with lower bounds. So before we do our lower bounds, we need to revise our Morse circles. Remember, for Morse circles and only Morse circles, we use a funny sign convention in which compressive stresses are positive, like these. Anti-clockwise shear stresses are positive, but clockwise shear stresses, clockwise, are negative. You would not use the same sign convention if you were resolving forces, because that might be a positive force and that a negative force. But we're not. We're drawing Morse circles, and only if you do that, if you use this sign convention, will the stresses acting on any plane plot as a circle. So the stresses acting on these two orthogonal planes plot diametrically opposite each other on a circle. In other materials, they might use other sign conventions. It doesn't matter what sign convention you use, you'll always get the right answer, providing you're consistent. But of course, within one subject like soil mechanics, we'd better use the same signs, otherwise we won't know what each other are talking about. So if I rotate that element of soil, then the stresses that are plotted down here for the two faces, they will trace out a circle as we rotate the square. Remember that the pairs of stresses which are at 90 degrees in space plot at 180 degrees, double the angle on the Morse circle. There will be one specific rotation like this, where the stresses will be principal stresses and the shear stresses here and here will be zero. The major principal stress and the minor principal stress. Okay, I hope that is all revision. Here's a little bit more. Slightly more complicated example. This is, for example, the stress distribution behind a retaining wall, considering one plane, this green plane. The stresses in the ground might be principal stresses, vertical and horizontal, quite typical in the ground as often. And we want to know what the stresses are on this particular plane, red and blue. So, because that's a principal stress, the vertical stress, there'll be no shearing on that plane, nor no shearing on that plane. They are principal stresses. So, this is the shear plane that you've just seen, and this is a Morse circle with the principal stresses. And if I want to know what the stresses are on that plane, what I've got to do is draw a line on my Morse circle that's parallel to that plane. That's a line at angle theta. Not quite drawn very well here, but that's the angle theta. And we're drawing a line from what we will discover to be the pole, and where it touches the Morse circle, those will be the stresses on our plane, sigma theta and tau theta. Now, I said that this is a pole. How do I know that that's a pole? Well, remember that lines drawn parallel to a plane, that should be parallel, on which the stresses act. So this is a plane on which these stresses are acting. They will all, for all planes, intersect at that pole. So it doesn't matter what angle I choose through here, all those planes will originate at that pole there. So, for example, let's consider the major principal stress, the vertical one, sigma 1. That is acting on a horizontal plane. So sigma 1, I draw a horizontal line and it should go to the pole. There it does. Sigma 3, horizontal stress, the minor principal stress, is acting on a vertical plane. So I draw a vertical line on my Morse circle, and it only goes through the Morse circle at one point, again confirming that's the point of the pole. So there indeed must be my pole. So the origin of planes, or pole, is the intersection of all planes in the element. So any plane that I can consider must originate at this point. So if I want the stresses on a plane like that, I draw a line like that, and that will be the stresses on those planes, always drawing from the pole. We applied more circles, remember, for triaxial test. This is just a bit of brief revision for you. Remember, in a triaxial, you've got axial and radial stress. Pore pressure inside the sample is U. And then we could draw more circles for a drain test. We did this not long ago. So total stresses without the dash, effective stresses with the dash. So the total stresses and effective stress, more circles open out like that as the test proceeds. And remember, it's the effective stresses, more circles that hit the failure envelope. And that will be your failure plane, where the Morse circle touches the failure plane, the phi dash plane, and that's the pole. So that will be your failure plane that you find in the sample, the failure plane there, because that is the pole of the Morse circle. So the pole in a triaxial test is at sigma r dash. Anyway, hopefully that's all revision about Morse circles. Now let's move on to lower bands. The thing about lower bands, or the formal statement, is that if an equilibrium state of stress can be found, which balances the applied loads and is everywhere below failure, then the structure cannot collapse. It is therefore a lower bound and must be a safe load. So you're just looking for a legal distribution of stresses which is in equilibrium. Doesn't have to be realistic, just has to be legal. And it's not failing, then it means you've found a distribution that must be safe. Put simply, if a body can support the applied loads, it will. In the lower bound method, we say nothing about compatibility at all. Nothing is moving, nothing is failing. We're on the point of failure, but nothing's failing. The lower bounds are all about equilibrium. We're checking equilibrium. We also check that the stresses are just on the point of failure so that we have stability. So we are considering material properties because we're considering strength. So we need an equilibrium state of stress. It can be realistic or not realistic. It just matters whether it's permissible or allowable. It doesn't matter whether it's realistic or not. In fact, you'll see they're not realistic at all. The stresses may vary smoothly, or they may just suddenly jump from one location to the next. Sudden jumps are fine. It's not realistic, but it is allowable. You're not breaking any laws by doing it. More circles may touch, but don't cross the failure envelope, and the soil is just about to fail. It's just about touching, but it's actually not failing. Nothing's moving. The stress discontinuities are just boundaries between zones with different stresses in them. They are not slip planes, like in the upper bound. There is no mechanism, nothing is failing. This is a lower bound, so of course we've got to maximize the solution to optimize it. So let's start with a very, very simple one. It's going to be easier to understand this by doing examples. So this is an example for our foundation, strip foundation again. So it's going to an infinite distance into the slide with a pressure P or stress P on it, with a breadth B, infinitely long. And I'm going to put a line through the soil that goes to infinity. And I'm going to use one line, one stress discontinuity. The whole thing's symmetrical, so I've got one on the other side, but we just consider one side. So that's a discontinuity. It means that the stresses here in this zone 1 and the stresses here in zone 2 are different. Now you know, because you've done it with Petra, I think you'll have thought about Boussinesq pressure distributions and seen how the pressure in the soil beneath the foundation will vary, and there's a sort of a bulb shape of pressure distribution, and the stresses would be maximum somewhere here and sort of decrease out this way. Forget all that. We are just thinking about what is permissible, and I am going to say but we're going to assume that the soil is weightless. So all of the stresses in this zone are one set of stresses, all of the stresses in this zone are another set of stresses, and we don't care if it's not realistic. We don't mind. So what could the stresses legally be? Well, in zone 1, we know, because the soil is weightless, remember, in this, that the vertical stress is going to be 0. So put a data point there, vertical stress in zone 1 is 0 there. I want to maximize this solution, so what is the maximum horizontal stress I could have? Well, the maximum horizontal stress I could have is if that Mohr circle just touches the failure envelope undrained shear strength SU, and so that would mean the horizontal stress would be 2SU. 2SU. That's the biggest Mohr circle I can possibly have and the maximum difference of the stresses. I know that for equilibrium, I must have the same horizontal stress in zone 2 as zone 1. Otherwise, something's going to move. So the horizontal stress in zone 1 is 2SU, so the horizontal stress in zone 2 must also be 2SU. Put here. And then in zone 2, again, to maximize the stresses, this is a lower bound, I need to maximize things, my Mohr circle would just touch the failure envelope, which means that the sigma V in zone 2 would be 4SU. 4SU. So we're maximizing our values so that P, the foundation load, will be 4SU, which is there. And both of our Mohr circles are just about touching the failure envelope SU. Now, this is complete rubbish as a stress distribution. Stresses beneath the real foundation won't look anything like this, but it's legal. In both zones, I'm just reaching the maximum stresses I'm allowed. There's equilibrium across this discontinuity. The stresses jump suddenly from this zone to this zone, but it's all legal. And you notice that the answer I get, 4SU, is pretty good already. I'm looking for 5.14 SU, remember? And it's already 4. Okay, I'm 25% off, but I've just put one line on a page to get it. Pretty good. So don't forget, stress discontinuities are simply boundaries between zones of soil with different stresses. They are not shear planes. That's not a mechanism. That goes to infinity. Nothing can move here. The consideration of equilibrium is a lot more rigorous than in limit equilibrium methods, which we'll have a look at later, because we are checking that the stresses in the soil are in equilibrium, not just that the forces applied in some global system are in equilibrium. As I said, the problem's symmetrical, so I only need to consider one side. So I'm going to say this is one discontinuity. I'm just considering one side for symmetry. In your tutorial sheet, you've got this example of 3 discontinuities, and I want you to have a go at it. We'll do it together eventually. But there are 3 discontinuities, and the angles between them are 30 degrees, and you have to start in zone 1, let's call it, and you work through to zone 2, zone 3, and zone 4 to get the foundation stress P. Okay, it's actually not that difficult. Let me just go through the sort of methodology. The order in which the calculation should proceed is always this. Firstly, draw the Mohr circle for the next zone. Well, we'll start with the first zone. Identify the pole of the Mohr circle that you've just drawn using stresses that you know. Using the pole, then identify the stresses on the boundary. So you draw a Mohr circle for this zone, you identify the pole using the stresses you know, which will be the vertical and horizontal stress. The vertical stress is 0, the horizontal stress might be 2SU. You can use the pole using those, you can get the pole using those stresses. Then use that pole to get the stresses on this discontinuity. Having got that, you know that the stresses on that discontinuity are the same whether you consider this zone or this zone. So then you can construct a Moore circle for this zone. You loop round. So you draw the Moore circle for the next zone. Identify the pole for this zone using the stresses you know. You know the stresses on that discontinuity, so you can get the pole for this zone. Use that pole to identify the stresses on the next boundary, the next discontinuity, which will be that one, etc., etc. And you just keep going around until you get to the foundation. Okay, you have a go, and then we'll try it together. So I'm going to go through the example of the 2 discontinuities, which is rather more difficult than the example for 3 that you've got to do. Okay, first thing we've got to do is consider the stresses in zone 1, which is here. Initially, I'm going to start with a Moore circle that's not failing, and we'll make it fail later. The vertical stress, remember the soil is weightless, the vertical stress in zone 1 is 0. That stress is acting on a horizontal plane, so the pole for zone 1 must be there. Now I need the stresses on this discontinuity. Remember, the next thing to do is to get the stresses on the next discontinuity, which is there. So from the pole, we draw a line parallel to that discontinuity, and where it crosses a Moore circle, that must be the stresses on that discontinuity, discontinuity 1, 2. The stresses on that discontinuity must be the same whether I consider zone 1 or zone 2. So the Moore circle for zone 2 must go through that same point. That Moore circle I will make fail. So it's now just about fail. It's just touching the undrained failure envelope. So there's only one Moore circle that just touches the failure and goes through that point, which is this one here. What do I need to do next? Well, I need now the pole for that circle. I know one set of stresses, which is the set of stresses on that plane. So from that Moore circle, I consider those stresses, draw a line parallel with that plane, which is this same line, and where it crosses my Moore circle, that must be the pole. So that's the pole for 2. What do I do next? Well, I've got to consider now the stresses on the next discontinuity, which is 2, 3, there. So I've got to draw a line from the pole for 2 parallel to that line, which is from the pole for 2 going up here somewhere. Symmetrical, of course. Where it crosses the Moore circle, those must be the stresses on discontinuity 2, 3. Discontinuity 2, 3. Those stresses will be the same whether I consider zone 3 or zone 2, because there must be equilibrium across this discontinuity. So the Moore circle for zone 3 must go through that point, and for now I will make it just symmetrical with the Moore circle for zone 1, a smaller one like that. We'll maximize it later. Then, of course, the vertical stress in zone 3 will be the foundation stress P. Oh, incidentally, the pole for zone 3 will be there. How do we get it? Well, for the Moore circle on zone 3, we consider the stresses that we know, which are these ones here. And from the stresses we know, we project down that same line that we had before, and where it intersects the Moore circle must be there. So, for example, the vertical stress, P, acts on a horizontal plane. So again, the horizontal plane will go through the same pole, which it must do. That's just a construction line at angle theta. This is the same theta here. And if you work through the geometry of it all, that will be SU tan theta. This will be a mess. This is symmetrical, so you've got to multiply all this by 2 to get P. So P is 2 times that lot, which gives you something like that. You can maximize the solution, and the maximized solution will be when that lot, this, becomes 2SU, when that does fail. but of course the angles would be a bit strange, and the angles are pi over 8, theta is pi over 8, so this in fact will be 45 degrees in here. Each theta is 22.5 degrees. But the more circles will look a bit messy. That will become 2SU, so it will touch there, and that will be 22.5 degrees in there. And if you do all that, you'll get P, the foundation stress is 4.83 SU, because you've got SU tan theta here, tan 22.5 degrees is 0.41 something. So that's where the 4.83 is coming from. That was a very complicated solution. That's much better than one discontinuity. One discontinuity gave you 4SU, but you're going to see that the solution for 3 discontinuities is much better and very close to the real answer. I think it's 5SU if I'm not wrong. And the 3 discontinuity one is much easier to do in this. You don't have to maximize anything, and the angles will not be difficult on your Morse circles. They'll be very easy. But you have a go at 3 discontinuities. The next few slides are for your entertainment, and those of you that are keen mathematicians may want to go through them. For those of us that are less keen, you can simply skip over and I will show you the answer, which is here. We only really need to know the answer, but please go through them if you want to understand the mathematics. If I have a stress discontinuity and the major principal stress in this zone A acting on that plane, so the stress is acting on a plane that's at right angles to the direction of the stress, and the angle of rotation is from theta A to theta B, and the major principal stress is acting on this plane in zone B. Well, the jump in the direction of the major principal stress, so the change of the angle here, so for a jump in the direction of the major principal stress of delta theta, that's the change of angle, the increase in the mean effective stress is, now S2 and S1, those are the centers of the Morse circles. So the change of the Morse circles is 2SU sine delta theta. That's a key result. And if that's infinitesimal, so if you have an infinitesimal change of this angle here, theta, then this becomes 2SU theta, or delta theta as I've written there. Okay, those are key results that will now apply. What this means is this. If I have a major principal stress in zone A acting on that plane, and that's 30 degrees, as it goes into zone B, it will change to 60 degrees, and the stress will change by SU. So, if delta theta is 30 degrees, then sine of 30 is what? Well, it's a half. So you get SB minus SA is SU, the undrained shear strength, which means that as I go from zone A to zone B, the stresses just increase by SU. And so the minor principal stress will increase by SU, the major principal stress will increase by SU. The centers of the Morse circle will move by SU. S, remember, is the center of the Morse circle. Everything changes by SU. So you can think of useful patterns, and we'll use these in examples in the tutorials. If I use 3 discontinuities, which remember looks like exactly the example you've got in your tutorial, I might have sigma 1 horizontal out here. That's approaching at 60 degrees, or you can think like here, the plane on which it acts, is at 30 degrees. So that is like this. So what have I got to do as I go past this discontinuity? The major principal stress will rotate by 30 degrees, and it will increase by SU. That's because the discontinuity is at 30 degrees like this. That one is now approaching this discontinuity in the same geometry. That's 60 degrees, or if you want to think in terms of the plane it's acting on, that's at 30 degrees, like that. Same thing. The stress will increase by SU, so now it becomes sigma 1 plus 2SU. That's at 30-degree rotation. And again, you're doing the same thing with the next discontinuity there. So you end up, as you go through 3 discontinuities, just rotating by 3 times 30 degrees. So you've gone from horizontal to vertical, and you've added 3SU. So whatever this stress was, this is the same stress plus 3SU. It's marvelous, and that makes lower bands very easy. So lower bands become very, very easy if the angles are 30 degrees on your discontinuities. This is another pattern that might be useful. There's sigma 1 in this zone. That's approaching this line at 60 degrees, or the plane on which it acts is approaching at 30 degrees. So we rotate by 30 degrees, add SU, but now we're approaching the other way to this discontinuity. So you add SU, but you rotate backwards. So you go from vertical sigma 1 to vertical sigma 1 plus 2SU. And whichever way we go round, that way, over that way, we'll get the same answer, of course. Here, I'm using arrows to indicate direction of sigma 1. But in shorthand notation, we often just put a cross with sigma 1 the long side of the cross and sigma 3 the short side of the cross. We'll see that in a minute. So here is the final answer. Remember that we've done 1 discontinuity, we've done 2 discontinuities. We did the 3 in the tutorial for you to have a go at. Now we've got infinite discontinuities. So we've got a fan zone of discontinuities, a bit like the fan zone we had for the mechanism. But remember that these is not a mechanism. These are just lines representing change of stress from one side to the other side. But because there are an infinite number of these discontinuities, the change of stress as we go from here through the fan zone to here varies smoothly. It's still not realistic, it's still not what would happen in reality, but there is a smooth change as we go through the fan zone. It's not changing in jumps because the jumps are infinitesimal. Remember, these discontinuities just extend forever. So zone 1 is a zone of unique stress. All the stresses are the same in zone 1. Zone 2, the stresses are varying slowly as we go through here. And then zone 3 is a zone where all the stresses are the same. Okay. We start like before. In zone 1, we know the vertical stress must be the minor principal stress and we'll have 0 stress. Like the 1 discontinuity example and the 3, we can maximize these stresses in zone 1. We couldn't do it for 2 discontinuities, but here we can. So we will have a Mohr circle that just touches failure, and so the horizontal stress in zone 1 will be 2SU. Note the use of the cross notation. So that's sigma 3, that's sigma 1. The pole in zone 1, now remember the vertical stress is 0 and it's acting on a horizontal plane. So from the pole we should be able to draw a horizontal line and we get to the vertical stress. So from the vertical stress, draw a horizontal line, we'll get to the pole. The stresses on that first discontinuity of the fan zone, well, to get those, we draw from the pole with a line at the same angle, and we'll get to the top of the Mohr circle because this is 45 degrees. As we go through the fan zone, there will be an infinite number of Mohr circles corresponding to the infinite number of discontinuities, and then we emerge out the other side, up here. That is the Mohr circle for zone number 3. Zone number 3 here. And that is the discontinuity that's there. The pole for zone 3 is there because the vertical stress acts on a horizontal plane. Vertical stress acts on a horizontal plane. So from the vertical stress, draw a line horizontally, we'll get to the pole, which is there. Those are the stresses on that last discontinuity there, because from the pole we draw a line at pi over 4, we'll get to those stresses which are those on that discontinuity. Now, from the proof that we didn't go through in detail, we know that if the stresses rotate by 90 degrees, pi over 2, that is because the included angle of the fan zone is 90 degrees. So these stresses are rotating by the same angle as that included angle of the fan zone. That's 90 degrees, so the stresses rotate 90 degrees. The Moore circle, as we go through the fan zone, changes by 2su theta. Theta's that angle there, the included angle of the fan zone. That's pi over 2. So the center of the Moore circle, from S3 to S1, changes by 2su theta, 2su pi over 2, which is pi su. So you can see where the solution's coming. That's su, that's pi su, that's su, and we've got our 5.14 su. So there we are, with the lower bound giving you exactly the same answer as the upper bound. So the solution is exact. Upper and lower bounds have given you exactly the same answer. This is called a complete bound because they give you the same answer. That generally won't be true. Upper and lower bounds won't give you the same answer. But you can see how relatively simple methods can give you very powerful answers. Just contrast that with limit equilibrium. Well, in limit equilibrium, we construct any mechanism. We have no real consideration of compatibility. So there's no real constriction or restriction on the mechanism chosen. You can choose whatever you want. You just choose any mechanism. In upper bounds, there were constrictions on them and restrictions on the mechanism, particularly in drained examples, which we didn't do. In the limit equilibrium, we just put torr is equal to su on all the slip planes and look for equilibrium in the large by resolving forces, taking moments for the whole structure. We do not consider any of the stresses in the soil. We ignore them. We examine all the mechanisms we can think about and find the minimum loads. That we don't consider any energy dissipation at all, like an upper bound. So for a strip footing, we might have a circular mechanism, just like an upper bound, but it would work like this for limit equilibrium. There's a force on the foundation F, B is the breadth of the foundation, O is the center of the circular failure mechanism. F, of course, is a force, and likewise, T will be the force arising from these shear stresses, which will be Su on the slip plane. So T will be torr, the shear stress, multiplied by pi b. Pi b is going to be the length. Sigma r is the radial stress on this slit surface. Now there'll be sigma r acting all the way around, and we don't know what they are, so that's a problem. But what we can do is take moments about O to eliminate the unknown sigma r. Remember, the sigma r in all directions, but they're all going through that point, so we can forget about them if we take moments about O. We'll get Fb over 2 is Tb equals pi b squared Su. We're going to end up with the force is going to be 2 pi b Su. That happens to be the same as the upper bound. It's a bit unfortunate, really, because this limit equilibrium is a positively hideous method, and the upper bound you've seen is very powerful. You could not get your 5.14 with limit equilibrium. But in that case, I hope I've shown you how limit equilibrium, you can get some sort of answer, but you're rather limited in what you can do. You've used it in slip circles for slopes and things like that.